a PhD at University of Chicago, Libby, and spent time at Princeton and University of Kansas before coming here to UCI as founding chairman. You have to forgive me, I just ran to my office and back. And he came here initially interested in radioisotope chemistry, and then his interest turned to atmospheric science, and as they say, the rest is history. He has been honored with a number of awards, including he is a member of the National Academy. He has been president of the American Association for the Advancement of Science. Recently, UCI gave him its highest honor, at least to my mind. He has his own parking space out under a pine tree out there. And today he will talk about two atmospheric problems: climate change and ozone depletion.
I think the first thing to say is we should take a good look now, because when we turn the lights down, you're not going to see me again for about an hour or so. And I'm talking about two atmospheric problems, and I want to make sure that everybody realizes that they are separate, and that is ozone depletion and global warming. Now, the only thing that means they're not separate is they're both taking place in the same atmosphere at the same time. And so there are some interactions between the two. But by and large, we're looking at two separate problems, one involving ultraviolet radiation and one involving infrared radiation. And with that, I'll say goodbye. And we'll get the first slide. The energy coming from the sun peaks in the visible region. And the energies that are involved in the visible region correspond to about 2 electron volts over here in the red and 4 electron volts in the ultraviolet. Now, the strengths of chemical bonds are usually several electron volts, so that if absorbing an individual quantum of radiation is going to cause a molecule to break apart, then you have to be in the 4 or 5 electron volt range, or even better out here in the ultraviolet. So that the destruction of molecules by single hits of radiation come over here in the ultraviolet, or sometimes in the violet. On the other hand, if you get down in the 2 electron volt or less range, then very few molecules will break apart when they absorb that. But that radiation that they do absorb has been intercepted. And that intercepted radiation can then be re-emitted. But it will be re-emitted in all directions. And if the radiation is coming up from the surface and is intercepted and then goes in all directions, a substantial fraction will go down. And in that sense, the radiation is prevented from getting out. And so what we're looking at then over here is ultraviolet radiation coming in, destroying molecules. And over here, we're looking at infrared radiation from the Earth trying to escape and being intercepted by molecules. And so those are the distinctions. Over here is ozone depletion, over here is global warming. And now, if we get back to the ozone itself, what we're looking at here is that molecular oxygen, which is 21% of the atmosphere, can absorb ultraviolet radiation, starting at 242 nanometers, but being very strong down around 195 and so on, down in this region. And when molecular oxygen absorbs ultraviolet radiation, it splits into 2 atoms of oxygen. Each of these oxygen atoms usually then finds another O2 molecule and makes the triatomic form of oxygen known as ozone. So as long as the sun is shining and we have oxygen in the atmosphere, we're going to have ozone. That's a condition that has prevailed for the Earth for more than 1 billion years. So everything that has grown up in the time period of the last 1 billion years has done so under the protection of the ozone shield, which takes out ultraviolet radiation at wavelengths below about 290 nanometers. This means, for as far as chemistry is concerned, if you put a molecule into the atmosphere, it's a very sharp distinction as to whether or not it absorbs anywhere beyond 290 nanometers out in this region. If it absorbs out in here, it's likely to break up, likely to have a fairly short lifetime. If it doesn't, if it only absorbs down in this region, then since it's protected by the ozone, it's not going to go away until it gets to an altitude where it's above most of the O2 and most of the O3. And that's the case with the chlorofluorocarbon compounds, whose absorption spectra start at around 220 nanometers and get stronger as you go down. The basic measurement technique used since the 1920s for measuring ozone in the atmosphere takes advantage of the fact that the absorption cross-sections for ozone are different and are varying with wavelength as you go through the ultraviolet region. If you're at 311 nanometers, then this is a level of radiation which is frequently absorbed, sometimes gets through, so that there will be a diminution in the strength of that radiation as you go through and take it to a detector. If you're at 332 nanometers, almost all of that radiation gets through. And so the standard technique has been to measure the ratio of, let's say, 311 nanometers to 332 nanometers. You take that ratio, put the solar zenith angle in it, and you can calculate how much ozone there is there, because the only important absorber of that radiation in the atmosphere is ozone itself. Most of the ozone is in the stratosphere above us, about 90%. And so this is a way of measuring what's in the stratosphere, but doing it from ground level. It's a technique that was invented by Dobson back in the 1920s. The ultraviolet spectrometer was known before that, but what Dobson did was to develop a way in which technicians could use this on a regular basis by putting in a wedge that would reduce this intensity to match this, and then you could read off the ozone from it. It's a standard instrument from the 1920s on. It's still the standard instrument for most of the ground-based measurements of ozone. With those measurements, what one finds is that the average amount of ozone over substantial periods of time, this would be averages, say, up to 1970, and it hasn't changed that much in terms of the qualitative scale that you have here. What one sees is that in the northern hemisphere, the amount of ozone peaks in March and April. And the amount of ozone that you find increases the further north you go. Now, in some respects, that sounds rather strange, because ozone is made by solar radiation. But what you find is that the largest concentrations of ozone are found at the end of a period when there hasn't been any solar radiation. That is, in the polar darkness up here in Leningrad. The number in Spitsbergen at 78 degrees north is a little bit off scale on this. And so this is not a paradox. It's because the destruction of ozone also requires solar radiation. So the matching up of producing and destroying of the solar radiation is moderated by the meteorology that carries air masses with ozone in it, and it's the meteorology carrying ozone into the polar regions where it slowly descends that lead eventually to this accumulation with the maximum in March and April. In Aspendale, which is near Melbourne in Australia, a similar pattern is true for the southern hemisphere, but laid out in just 6 months out of phase. It's still at the end of the long winter, but now the end of the long winter in the southern hemisphere is September and October. And then in the tropics, one finds, and as Moncayo is in Peru, what one finds is that there's not much variation month to month or day to day. It's a very nearly constant kind of ozone measurement present there from day to day, month to month, and year to year. This is the Halley Bay Station of the British Antarctic Survey. This was established in preparation for the International Geophysical Year, and what they did was to set up an ozone measuring device there, the Dobson spectrometer, and proceeded then to start making measurements. And this is the kind of measurement that they saw. Going down to Antarctica at that time, they had no real preconception as to what they should see, except, so they said, well, the northern hemisphere and the southern hemisphere probably should be symmetric, and have the peak of ozone coming, as we just said, September and October in the southern hemisphere, the way it was in Australia. And this is the Spitsbergen curve that's 78 degrees north, with a peak at around 480 Dobson units. Displaced 6 months, so that it says show where if you had the Spitsbergen curve, this is what you would have seen in Antarctica. And that's not what they saw. What they saw instead was that they had about 300 Dobson units in that time period. Now, a Dobson unit is approximately 1 part in 10 to the 9th. And so 300 Dobson units, and it is about the average value for the whole world. So what they had was an average amount of ozone over Antarctica through the winter and into the period of early spring, which would be October. And then in mid-November, the amount suddenly jumped up and then followed the pattern that you see in Spitsbergen here, followed that pattern on, and these are moonlight measurements here, followed that pattern on and was repeated in that year, and was repeated and repeated for quite a number of years after that. So, and what this amounted to was discovering that the northern hemisphere and the southern hemisphere were not symmetric in their ozone measurements, that in the southern hemisphere there is a very intense polar vortex, such that the air that's in the stratosphere at the beginning of the winter stays there all winter long and halfway through spring, and then finally breaks up, and ozone-laden air comes in from the temperate zone, and that's what you're seeing here. It's not that ozone has been made over Antarctica, it's that ozone has finally managed to penetrate, coming in from the temperate zone, pushing out this lower ozone air here. Well, this was a measurement then made, starting to be made in the 1950s, and it's the beginning of looking at the atmospheric chemistry that we're looking at now. At the same time, in the International Geophysical Year, Dave Keeling at the Scripps Institute of Oceanography started measuring carbon dioxide and measured it at Mauna Loa in Hawaii. And what one sees is that when he started measurement, the first year, 1958, what you see is that the average value was about 315 parts per million. But it peaked along in March or April, and then fell all during the spring and summer, and then in the autumn turned around and started up again. And so what you're seeing is a seasonal cycle that corresponds to photosynthesis in the northern hemisphere. The green plants are growing, they're using carbon dioxide, it takes the carbon dioxide out of the atmosphere. All during the year, there is decomposition going on that puts carbon dioxide back in the atmosphere. And so what one has is a balance, but you find it's not quite a balance, that at the end of the year, get back to the same month here and repeating it, that the amount of carbon dioxide is progressively slightly larger each year as you go on. And so by 1970, what one sees is that instead of 315 parts per million, the number was more like 326 parts per million. And so what Keeling had demonstrated was that the amount of carbon dioxide in the atmosphere was changing. It was following this cyclic behavior, but the amount was going up all of the time. And that's attributed to the burning of fossil fuel, of coal, gas, and oil, and producing carbon dioxide and adding to the carbon dioxide burden that you go on there. The beginning of the chlorofluorocarbon story really is shown here. A scientist, Jim Lovelock, in Great Britain, invented a very sensitive detector, the electron capture detector. And first he set it up at his home in Western Ireland and showed that every air sample that he took had in it this one compound, trichlorofluoromethane, which is also known as CFC11, a chlorofluorocarbon. It's a freon 11 if it's made by the DuPont company. And what he showed first was that every sample he tried in Ireland had this compound in it. Then he put the detector on board a ship heading for Antarctica and proceeded to make measurements, and every air sample he took on board the ship also had this material in it. Now, it's a material that's made by man, it's manufactured specifically because it is inert, for use as an inert carrier in various uses. The uses back in the 1970s, the major use in the United States was a propellant gas for aerosol sprays, but it was also until the last 2 or 3 years, the refrigerant gas in your automobile air conditioner, the refrigerant gas in your home refrigerator. And another CFC is used for cleaning stereo components for microelectronics. And so this is a material that put into the atmosphere, but put into it because it was inert for the technological use that this was where, in 1973, Mario Molina, who's shown here, was a postdoc. This is Louisa Molina and Bill Smith, two other postdocs at that time. But Mario took on the proposed problem of, I proposed to him, let's find out what's going to happen to the chlorofluorocarbons in the atmosphere. And so we started out, and that was in October of 1973. And these are the considerations that one takes for most organic molecules that go into the atmosphere. First, if it's molecular chlorine, it's a green gas. That means it's intercepting visible radiation. When it does so, it splits apart, and you get chlorine atoms. We call that a sink, and because it happens in the lower atmosphere, it's a tropospheric sink. It takes about an hour in sunlight. Hydrogen chloride is a transparent gas, which means it doesn't interact with visible radiation. Neither does it absorb any the infrared or the ultraviolet radiation that's available at the surface of the Earth, so it doesn't photolize in the lower atmosphere. But it's a polar molecule, it dissolves in water, and when the raindrops fall, the hydrogen chloride gets carried out as hydrochloric acid. And the third process, common process, is the reaction with an oxidizing agent. It's illustrated here with methyl chloride. If there's a carbon-hydrogen bond in a molecule, usually something like hydroxyl radical will be able to pull it off. And for methyl chloride, this is the same, takes about a year and a half on the average in the lower atmosphere. But trichlorofluoromethane is transparent, nonpolar, so it doesn't dissolve, doesn't react with oxidizing agents, and so that means none of these things will cause it to cause the molecule to be removed. If we go back in a cartoon version saying what does the ozone layer do for us, it basically does two things. One is it prevents some of the ultraviolet radiation, especially the short wavelength ultraviolet radiation below 290 nanometers of getting to the surface of the Earth. And the other thing it does is when ozone absorbs ultraviolet radiation, it splits off an oxygen atom, which usually then finds an O2 molecule and reforms ozone. So that doesn't get rid of ozone. What it does is convert the ultraviolet energy into heat, and that creates what we call the stratosphere. A region in which, because there's a heat source up in here, in which the temperature of the atmosphere rises as you go up with altitude. So the stratosphere depends intimately on the presence of ozone because it's the heat source that creates this particular temperature structure. Well, if you continue to ask what can happen to the chlorofluorocarbons, one of the things that can happen is to absorb ultraviolet radiation if it's less than 220 nanometers. But to see that radiation, it's got to be above most of the O2 and most of the O3. If it does see it, then what it's going to do is absorb that light, and it splits apart and produces a chlorine atom. Now, there's a big difference between the reactivity of trichlorofluoromethane, which is a very inert molecule, and chlorine atom, which is the extremely reactive molecule. Chlorine atom then has been produced, but it's going to be produced it's closely related to the ozone layer itself because the molecule has to have gotten above most of the ozone before this reaction can even happen. And so the chlorine atom is going to be produced near the top of the ozone layer and eventually would have to wander its way back down to the surface of the Earth. The dichlorodifluoromethane compound, also an important aerosol material. I'm sorry, when I said before, fluorocarbon 11, fluorocarbon 12 is your home refrigerant unless your refrigerator was recently purchased. Fluorocarbon 11 and fluorocarbon 12 were aerosol propellants, and all of them have the same kind of characteristic that they're inert. When we did a calculation in 1974 of what one should expect when you look in the atmosphere, it was that from the ground up to the tropopause, that is the top of the lower part of the atmosphere, that the mole fraction or the mixing ratio should be the same all the way up. And then as soon as it gets into the stratosphere where gases move very much more slowly, you should start seeing a fall off in its concentration, in its mole fraction, and by 30 kilometers it should be nearly gone. Well, this was a calculation that we made in '74. This is where the ozone is. This is where the chlorine is calculated as being formed. So we're looking at chlorine being produced in this altitude range here. And this is where the problem turned from being an interesting chemistry problem to us to being an environmental problem. And that's because when you ask what happens to the chlorine atom, you find out that chlorine attacks ozone, gives you chlorine oxide. Chlorine oxide intercepts some of these oxygen atoms which would otherwise have become ozone and gives you back the chlorine atom. This takes about 1 second in the stratosphere, less than a second. This takes about a minute, and you've got the chlorine ready to go again. Now there are some other chemical reactions that I'll talk about a little bit later, which divert the chlorine from this sequence for a while. But this sequence is such that over the time period before the chlorine atom gets back down again, about 100,000 molecules of ozone will be removed per chlorine atom. And it's taking about 1 million tons of CFCs put into the atmosphere every year in the 1970s and the 1980s, and multiplying it by 100,000. That put this on said this reaction, if we continued to put in the CFCs, would begin to be about equivalent to the rate of removal of ozone by natural processes. So that's summarized here, that the ozone layer has not only protected us and all the biological species here, but it protected the CFCs, and they have to get up above, and then this chain reaction can take place.
What are the natural processes?
Pardon?
What are the natural processes?
The natural processes are basically four in number. You have NO2, NO2 is one, HO, HO2. There is a natural source of chlorine, and then oxygen atoms and O3 can react with each other directly to form it. And all of those take place. And what this amounts to is that you're adding a substantial amount of a removal process to those that were already there. Now, the one republished in 1974, and of course there were immediate saying this is an interesting hypothesis, but it needs to be confirmed in the atmosphere. And this is one of the first confirmations, and that was done by two different research groups in Boulder, Colorado. These spheres, actually made out of salad bowls, were purchased in the local grocery store and put together. I think they were gold coated, however, so they would cost a little bit more. But down here are valves to control the pressure, and the next slide will show them being carried up on a balloon, and the next slide will show the results from that and from the other experiment. And what one finds is that the amount of the fluorocarbon 11, which is the one that's shown here, the amount of fluorocarbon 11 goes approximately as we calculated the year before. And it shows two things. One is that despite the fact they're heavier than air, the CFCs do get into the stratosphere. And that's because the mixing of the atmosphere takes place in large blocks. It's wind mixing by the winds rather than by molecular diffusion. And so the fact that it's heavier than air doesn't make any difference until you get way above the stratosphere. About 120 kilometers, you begin to get some gravitational separation by molecular weight. And the other thing is that they disappeared at about the wavelength, about the altitudes that we had calculated before. Well, another technique that you can use to start getting information about this is electron capture gas chromatography. Electron capture gas chromatography was the technique used by Lovelock in the first place. And we've been using that since 1973 for making measurements. This is a sample collected in the Netherlands in 1988. And what the electron capture gas chromatograph shows is, as a function of time, you can identify individual molecules. The individual molecules have different times coming out of this column. You put the air sample through a long column and force it essentially to go into solution and out of solution 100,000 times, and then the boiling point starts taking effect, and the ones with lower boiling points come out first. There are variations on that, but that's basically what's happening. And these green ones are the CFCs, fluorocarbon 12, the dichloro. This is the trichloro compound, and this is a trichloroethane, that is C2CL3F3. And the individual responses are different. And I have truncated here 7 of them. 7 of them go way on up, just to show you there are a lot of compounds in any city that you can actually measure. This is still true now, but in fact there's more of it than there was in 1988, but the amounts are no longer increasing. But if you're trying to find out how much there is in the world, which was the aim that we had at this point, what you need to do is not go to the cities where you know it's being released. You need to go to a lot of remote locations so that you can get an assay for the entire world. And so since about 1978, we have been going around collecting samples. This is Patricia Rogers on the island of Nauru back in the early 1980s. The next slide shows Tai Chen, who's not here today because he's printing out his thesis. And I was a little bit dismayed to read in his acknowledgments at the front of it that during the course of his PhD, he traveled to more than 30 countries. This is Pakistan. He's in the mountains above Islamabad, collecting an air sample there.
Do you need more volunteers?
Now, in doing these collections, then you go to a place like Barrow, Alaska. It's on the north slope of Alaska. This was 1983. If we focus on fluorocarbon 11 right here, we'll go on to the next slide, and you'll see how much there was. You can see that between 1983 and 1988, there was a substantial increase in the amount. In principle, and in fact, if you get a good measurement at enough locations, you can tell how much of this material is in the atmosphere, and therefore you compare it with how much has been put in, and come out with an estimate of its lifetime. Molina and I calculated 40 to 80-year lifetime in 1974. The current best estimate from the measurements in the atmosphere is 50 years. The dichloro-difluoro compound is about 100-year lifetime. And the total change in chlorine, it can be seen here. This is summer of 1979 with collections, and the number here is 170 parts per trillion. I didn't say, but when Lovelock measured in 1971, it was 70 in the northern hemisphere, and he had about 40 in the southern hemisphere. Here it's almost up to 160. And in 1987, I think is this one, what you see is that the amount is now about 250 in the northern hemisphere, and is 220 here at the South Pole. So that it's, and what one sees is that this is a gas which, with a long lifetime, it's almost all released to the atmosphere between 30 and 60 degrees north. But it has spread nearly uniformly around the world. And that's because it spends a long time before it goes to the stratosphere. When it does, it goes up in big storms at the equator. That's the way everything gets into the stratosphere. And this is the growth of the chlorine compounds. Carbon tetrachloride, methylchloroform, CFCs, a few others, and methyl chloride, which is mostly a natural material. And what we see is that in 1950, there was about 0.8 of a part per billion of chlorine, organic chlorine in the atmosphere. And now by 1990, we're approaching 4. So about 5 times as much here. If we went back to 1900, only this one down here, because carbon tet didn't come in until just before World War I. So this would be about 0.6 in 1900. At the same time that we had these canisters, we started measuring methane. And methane is what's shown here, northern hemisphere, southern hemisphere. And what you see is 1.6 parts per million, a little bit about 1.47 parts per million in the southern hemisphere. That was January 1978. We collected some more samples in the summer of 1979 and found that every place that we had collected in both years, that there was more in the northern hemisphere. And that meant we were often on something else that is looking at what happens to methane. By 1983, instead of being 1.6, it was 1.7. And that number has continued to go up, and I think the next slide will show, or it shows why, or at least it tells you where the methane is coming from without telling you necessarily why it's increasing. Methane comes from the rice paddies during the time that they're flooded. Some work by Ralph Cicerone has shown that the methane actually comes up through the plant, not out of the water. The plant is a conduit to getting methane from down below out into the atmosphere. I should have mention when we went by it that the chain reaction of chlorine with ozone was originally discovered by Cicerone and Stolarski, who were then at the University of Michigan, a few months before Melina and I started to work. And so here, one of the sources of methane is this one, a biological source from rice paddies, and another source is from cows. The standard figure is that a cow gives off about half a pound of methane per day, and there are about 1.3 billion cows in the world, and that ends up as being a substantial contributor to the total amount of methane in the atmosphere. And here are Don Blake's measurements now, going back to 1979 and coming up here, instead of 1550 in the middle of 1979, it's 1750 in the beginning of 1996. So there's been a steady increase in methane, and this becomes significant both for ozone depletion, where it can react with chlorine, and for global warming, where it can where the methane can intercept the infrared radiation that's coming from the atmosphere. Okay, I want to come back here and just comment again that the reason that the solar radiation peaks at around 500 nanometers is that the surface of the sun is about 6,000 degrees Kelvin. And that's if you're putting it into the black body formula, that comes out with around 500 nanometers as the peak in the radiation that's coming from it. As the temperature of the black body drops from 6,000, this peak moves in this direction. And if the temperature is around 300 Kelvin, which is a rough value for the Earth, then you will expect it to be from 6,000 to 300 Kelvin is a factor of 20, moves the radiation out by a factor of 20. Instead of peaking at 500 nanometers, it peaks at 10,000 nanometers, which is called 10 microns in the infrared world, which is where those measurements are. So around 10 microns is where the radiation is expected to peak. If one does a calculation, I'm going to use a term of the greenhouse effect and then the enhanced greenhouse effect. The greenhouse effect is, let's say, what you would have expected if you had done the calculation, let's say, in 1800, before the people of the world started burning fossil fuels. And then one would ask the other question, well, now that we have doing it, what change will that be? But first you want to find out what's going on as far as the black body effect on the Earth. And you can do a calculation here of coming out of the sun, 4 pi r squared for isotropic emission, pi r squared here in the cross-section intercepted by the Earth. So that'll give us a factor of 4, and the albedo of the Earth is about 30%. That is, about 30% of the incoming solar radiation is reflected back to space without being absorbed. If we look at do a calculation for the emission from the Earth, having absorbed it, that factor of 4 gets put in here, and what one sees is that the emitted radiation is 240 watts per square meter, and if you go on to the next and calculate then what temperature that should be if all of the radiation is getting out, what you come up with is 0 degrees Fahrenheit or minus 18 degrees centigrade as the average for the whole Earth. And what one observes is not 0 Fahrenheit, but more like 59 degrees Fahrenheit. And that means that there is a natural greenhouse effect, which has been there all along, and which warms the Earth by 33 degrees centigrade or 59 degrees Fahrenheit. About the only factor in this 1368 has been measured by several different satellites. That's the intensity of the radiation coming from the sun. There's that factor of 4, and the albedo has been subtracted here. So there's not a whole lot of leeway in here, as you could argue for a couple of degrees maybe. But basically, the Earth is much warmer than it would be if it were just a black body emitting the radiation. Now, the reason why it's much warmer is for the natural greenhouse effect. And what I've shown here is the fraction of the radiation from the sun as a function of the microns coming in, where 10 is going to be about the maximum. fraction that gets through with methane absorption and with ozone absorption here. Now, at this particular point, that says that only about 5% of that radiation gets through with the average amount of ozone in the atmosphere. Only about 25% of the methane radiation gets through here. But there are other regions where there's no absorption at all, and that's because the infrared absorption is going into specific vibrational modes of the polyatomic molecules, such as methane and ozone. And then you go on and you can look at nitrous oxide and carbon dioxide. Here's carbon dioxide blocking it out entirely. Over here is nitrous oxide. I think the next one will show water. And water blocked out a lot of regions in here, and you put them all together, and that comes out here. And what you see is that in the region around 10 microns, there is a more or less transparent region over here, and a nearly transparent one here, and a lot of regions where there is strong absorption. Now this happens, of course, to be where the peak of the radiation coming from the Earth comes out, but it's got strong absorptions biting into it. It says that if you were to observe this from outside, from space, then you ought to see this kind of effect. And of course that's been done, and that's shown on the next slide, where one sees an infrared spectrometer looking straight down. No, sorry. Looking straight down at the Sahara Desert. The temperature that it's seeing in the transparent region is 320 Kelvin, 117 Fahrenheit. So it's looking at the Sahara Desert. The radiation's coming out without being intercepted. This is radiation which can be intercepted by CO2, and what you're seeing is the radiation that finally gets out is being given out in the lower stratosphere, where the temperature is about 210 Kelvin. And here's the other transparent region over here. So, and this was actually taken in 1970. So it shows that this has been a steady pattern all along, that the natural greenhouse effect is there, and what the question being asked now is, as you change the amount of CO2, methane, so on, what do you do? How much do you augment the natural greenhouse effect? And that's the background on global warming. You can look at it in a different way, more qualitative, but here's visible radiation, the satellite looking down at the surface, and what you see is that there's a temperature difference between Africa and the ocean, but the main thing is you see both. And that means that radiation is getting out without being intercepted. Over here is the infrared in one of those transparent regions, and again, you can see the outline of Africa, which means that radiation is getting out without being intercepted. And here's a wavelength that's absorbed by water vapor, and that simply doesn't get out. All you see is the swirling of clouds. It's coming out from the tops of the clouds at this wavelength, and that doesn't tell you anything at the surface. So these wavelengths are not coming out, and instead, the Earth has to warm up to put the radiation out in the wavelengths over here in the infrared that can get out. And so that's just looking at the natural greenhouse effect here by the fact that there are some wavelengths that absorb and some that are getting out anyway. Going back to Halley Bay in Antarctica, in the late 1970s, after measuring 300 Dobson units, I showed you the first couple, but after measuring 300 Dobson units for 15 years or so, it started to fall off. And when it went down to below 200 in 1984, they published, it said something is happening in Antarctica. There's less ozone there in the month of October, first month of spring in the southern hemisphere. In the month of October, there was less ozone over Halley Bay than there had been in the previous years over a time period of almost 20 years. They also put here, they plotted the concentration, measured concentrations of chlorofluorocarbons in the negative direction, showing that in their view, there was a correlation between the amount of chlorofluorocarbon in the atmosphere and the loss of ozone. Now, there is another way of measuring ozone in the atmosphere, and that's shown here. It's the same principle. You're looking at two wavelengths of ultraviolet radiation, one that's absorbed by ozone, one that's not, and it's being backscattered from the troposphere, from the clouds or from the surface. And the radiation is coming back up, and you're looking at it, looking at the ratio with the Nimbus 7 satellite. And this is a demonstration of the measurements. A few 100,000 measurements a day. And starting in November 1st of 1979, this was then the 1st October, 1978. So it had been up about 11 months, and they started measuring. They were measuring in October. And this was 1979. With that many measurements, you put it in a color code, and the color code shows 500 Dobson units, and here about 250 to 275. Well, over this part of Antarctica, and Halley Bay sits right here, over this part of Antarctica, the value in 1979 was about 250 Dobson units. Down here, the brown is up to 500, the orange is above 450, so this is 450 to 500. And this is 60 degrees south latitude. Here's South America, Africa, and Australia. And they continue to make these measurements, and 4 years later, the first week in October, you could see this, and now the low value is somewhere between 175 and 200 Dobson units. And if you follow it another 4, what you see is that the low value had now fallen below 125 Dobson units. The blue, which was the middle value, was the low value in 8 years earlier, is now just a ring all the way around the outside of Antarctica. The brown that was a big blotch in the first one is now essentially gone, and most of the orange is gone as well. So there's been a substantial loss of ozone, not only in this polar vortex, but outside of it as well. And so this is confirmation that what was being observed at Halley Bay was also being seen in many other locations all over the Antarctic region. The chemistry in the temperate zone stratosphere involves the chlorine oxide interchange here that can take out ozone on each step. But there are these temporary reservoirs of HOCl, HCl, and chlorine nitrate that when the chlorine's in those forms, it's not removing ozone. And they're all present in the atmosphere in the temperate stratosphere. In the polar stratosphere, on the surfaces of the clouds that one finds there, some reactions take place, one of which is hydrogen chloride and chlorine nitrate react to produce molecular chlorine and nitric acid. The nitric acid goes into the clouds. In fact, all of the NO2 gas goes into the clouds. And so what one has as the sun comes up is molecular chlorine, which can absorb radiation, photolize, and starts producing chlorine. You get chlorine reacts with ozone, you get chlorine oxide, and you no longer have NO2 to take it out. And so this concentration jumps way up. It got high enough that it can react with itself, and a different chain reaction occurs in the polar regions. The temperate zone chain reaction depends on the presence of oxygen atoms, and there aren't very many in the polar regions when the sun is on the horizon. But you can go through this other mechanism that involves a chlorine oxide dimer, and that is the explanation for what's going on over in the Antarctic. Now, this is the ER-2 aircraft of NASA. It had on it that this was flying out of Punta Arenas in the southern tip of South America. Had on it an ozone measuring device and a device to measure chlorine oxide. And these are the results of 2 experiments in 1987. Jim Anderson at Harvard had the chlorine oxide experiment, and what you see is when they got out basically into the polar vortex out over Antarctica, the amount of chlorine oxide jumped way up. Now, Mike Prophet's ozone measuring device showed almost no change as you flew into that polar vortex. Now, this is August 23rd. It's a month away from equinox. It's still late winter. Sunlight has just begun to penetrate, so it's still been in the darkness. If you have molecular chlorine, it's only been dissociated for a couple of days at this point, and not much ozone loss has happened. But 3 weeks later, September 16th, what one finds is, again, as you get into the polar vortex, the chlorine oxide goes way up. But now 2/3 of the ozone is gone in that 3 weeks. And that's because this chain reaction runs almost unimpeded during that time. Unimpeded because the NO2 has been removed and is tied up in the clouds. And it's this, and on this particular day, the polar vortex was very ragged as they flew in. And so chlorine oxide went up and down a number of times before it finally went up to a high value. And ozone went down and up in mirror image to what was found down here, all the way until it got into the vortex, and then it was always low. And this particular, this is one of the most widely distributed figures that has been produced in the ozone case in the last 20 years, simply because it shows in the intimate detail of the correlation or the anti-correlation between chlorine oxide and ozone. Chlorine oxide is high, ozone is low, and it ties the destruction of ozone very firmly to the chlorine oxide present. Back in 1986, a graduate student here named Neil Paris, working with me, I asked him, the problem was that the statistical analyses of the data at Arosa in Switzerland, the statistical analyses that have been done said there's no ozone loss has happened there yet. Well, when I looked at the plot of the yearly data, it seemed to me that by eyeball it looked to me as though something had happened. And so I asked Neil to look at it to explain why my eyeball saw something differently than the statistical analysis. And what it turned out to depend upon was what is shown here. These are the measurements over a 56-year period here. And what one is looking at is that in the wintertime, January, February, March, there's a very large standard deviation. In the summertime, the natural deviation is very much smaller. And the statistical analysis has been set up, say, on the assumption that if you had a loss of ozone, then it would be the same in the summer and the winter. And the best place, if that's true, then the best place to look for it is where the natural deviation is least. So they biased their statistics. They used them all, but they've weighted these so much more heavily that they effectively were checking to see whether, from a statistical point of view, there had been a loss of ozone in the summer. Now, what Neil did was do something much simpler. He just averaged before 1970 and after 1970, subtracted one from the other, and came out that there was a 5% loss in the ozone in the northern hemisphere at Arosa. This is Rosa's in the Swiss Alps. And so this led to looking at all of the stations in the northern hemisphere. And this is the result as reported by the Ozone Trends Panel in 1988, that every station north of 35 degrees north, when you analyzed it by just simply taking the average before and after 1970, had lost ozone. And this changed the attitude of a lot of people, including the DuPont company. When the panel came out and said, we think the ozone is going away in the northern hemisphere as well, the DuPont company looked at it and said, basically, we quit. We're going to get out of this business. And once one company said they were going to get out, then all of the others followed suit very quickly. If here I'm showing what sometimes happens, this is first week in 1992, the polar vortex was very elongated. It swung out over South America here, so you got much lower ozone values there and very low ozone values in the Antarctic Peninsula, which is shown here. And this has to do with the ultraviolet radiation that can escape, can come through as a result of having less ozone. It is not very important for paint, because the effect of ultraviolet on paint doesn't change very much with wavelength. But for humans and for other biological species, it is very important because the absorption spectrum of DNA comes in, this is a factor of 1 million in scale. The absorption by DNA gets very strong as you get down around 300 nanometers and get into the 270, 280 nanometers here. At the same time that sunlight is falling off very rapidly, again on that same exponential scale of about 1 million, because of the absorption by ozone. So if you were to increase the amount of, if you reduce the amount of ozone, you make big increases down here, and because that's very effective as far as DNA is concerned, it increases what is called the UVB exposure of whatever biological species that is. These are measurements now that have been made this was 1992. Biospherical Instruments is a company in San Diego that has been doing measurements of ultraviolet radiation, not with the Dobson spectrometer, but one that makes absolute measurements. And when they measure over this is taken over the South Pole, you measure in the spring when the ozone hole is overhead, and in the fall when it's not, and you get a ratio. And what you can see is that when there's 50% less ozone, there's 300% more radiation in the UVB range. So it shows this is when you weight it with the absorption spectrum of DNA. But it shows very clearly that when there's less ozone, there's much more ultraviolet radiation. What they did was match solar zenith angles there. Here are some measurements taken right at the beginning of January of 1995 over Mauna Loa. Most of the time, the measurements indicate very little change in ozone in tropical regions. But at this particular time, there was an unusual meteorological event, and the ozone value, which, as I said before, for Huancayo in Peru, stays around 250, 260 all the time, day to day. And that's what it does in Mauna Loa, and here it was up in the 250, and then suddenly it dropped below 200, just a little bit below 200 here. And the amount of radiation at 295 nanometers tripled during that time period. So it says that here we have a situation in which things in the tropics may have been getting 3 times as much ultraviolet radiation for a few days as they did before. This is a series of measurements in 1993, and the most intense day in Southern California, that is in San Diego, was on June 21st of that year. The sun's nearly overhead. In fact, it's as close to overhead as it gets in Southern California. And this is the intensity of the UVB that day. And in an October day in the Antarctic Peninsula, this is the intensity that was seen. It was 25% greater on the most intense day in the Antarctica as it was in San Diego, which means that biological species in the Antarctic Peninsula are now exposed to tropical level of ozone, of ultraviolet radiation, because of the very low ozone. Even though the solar zenith angle was 52 degrees on that day, the sun was not overhead at all. But because it depends so strongly on ozone, very intense ultraviolet radiation there. Now, question of what the ultraviolet radiation does, and I don't want to go into any detail, but this is taken actually from Marjorie Casario's textbook about the DNA structure, the relationships of adenine and thymine, the bases that are attached to sugars. And what we'll look in the next slide is in a situation when you have 2 thymine molecules adjacent to each other. There's a double bond there, there's a double bond there, and the effect of ultraviolet B, one of the effects of ultraviolet B, is to cause this double bond and this double bond to expand and create a cyclobutane, which ties these 2 molecules together, two neighboring groups together, so that they no longer can move freely. What this does is induce errors in the coding of the molecule. Instead of picking up what it should over here and over here, sometimes mistakes occur, and this is then an ultraviolet B induced defect. In fact, if it stays on sufficiently until things get attracted here, then it's a genetic error, and one, depending on what's here, then something else may happen. So this is one of the effects of ultraviolet B on, not just on humans, because everyone has the DNA, and thymine is present there, so there are lots and lots of possibilities for this dimer, and there are quite a number of other defects of the same kind that are introduced by this kind of radiation. So that's why one worries about the effect of ultraviolet B on biological species. Okay, well, we have the Montreal Protocol, which was agreed to in 1987. The original agreement of the Montreal Protocol was to cut the production of CFCs in the first world by a factor of 2, that is 50% reduction by the end of the century, that is this century, so by the year 2000. And then in 1990 it was modified for 100% reduction by the end of the century. And in 1992 it was modified to 100% reduction by January 1 of 1996. That was more than 10 months ago. And so this is what one would have expected without any control, just putting it in at the same rate. This was the original Montreal Protocol, cutting it in half, and then a complete phase out would do this. This was for the phase out at near the end of the century, and so now the question is what's happening in the atmosphere, and these are the measurements that have been made at Cape Grim. These are the Australian measurements. We've made similar measurements, so have people in Colorado, and there are some minor differences, but no real difference. That in fact, methylchloroform is falling off in concentration. Fluorocarbon 11 is essentially constant. Carbon 10 is constant. The total has actually gone through a maximum. So now there is less chlorine bonded to carbon in the lower atmosphere than there was 5 years ago. And we expect it gradually to decrease. But it's going to decrease very slowly over all of the next century. In fact, the big decrease is getting rid of methylchloroform. Once it's out, then everything will go very much more slowly. Methylchloroform as a carbon-hydrogen bond has a lifetime in the atmosphere of about 5 years. Once you quit putting any in a matter of 10 or 15 years, almost all of it will be gone. A quick discussion of what we've been doing in the lab, or rather as part of our group. This is the NASA DC-8. We have, instead of taking individual canisters, we take 168 of them on board the airplane. You bring them back. This is Bradley Sive working at the analytical lab upstairs, having brought the samples back from wherever it was they were collected. This is where they were being collected in 6 weeks ago. This is Barclay and then 2 postdocs, Lisa McKenzie and Mick and Blake, on Easter Island. Later on, one of the things that one can run into is the fact that there now is a lot of burning going on in South America and in Africa. This is a picture of burning going on in South America. This was taken from one of the shuttles, and the area that's shown here is essentially Brazil. And it was in September of 1988, and they had a smoke cloud that covered the entire country. And this was when Yellowstone Park burned. This was about the size of the smoke cloud that came from it. But this is the smoke cloud in Brazil during the burning season. This was let's see, Don and Lisa and Jimmy Lopez, and we're all on this flight coming out of Fiji in October, I think, October 2nd, it says. What you see here is downward-looking LiDAR that measures ozone, and there's this plume here that is ozone, instead of being down around 20 or 30, which is where it is above and below it, but between 3 and 5 kilometers, they're flying north out of Fiji, the ozone was up around 100. This is the plume, biomass burning plume, coming all the way from South America over to Fiji and staying together like that. Later on, when it came up to the flight altitude, and they showed that all the hydrocarbons went up over the things which we measured. This was called a mission called Chemtropics, but it was interpreted very broadly. This shows the DC-8 as it was flying along the Antarctic coast. So that calling 72 degrees south part of tropics, it was symmetrical, because when we were on the Arctic mission, one of the most interesting flights was the one to Tahiti. So basically, when you get the airplane equipped, they try to take it every place. Well, come back to Keeling. Here are his measurements now into 1996. Instead of 315, now it's 360. There's been a steady increase in carbon dioxide all through that time. I've already shown you that methane had increased. And what one can do as well is to take samples out. This is the Calcaya Glacier in Peru, in which you can see annual layers here. And that is, the dust blows in during one season from Chile, and you get a dust layer, and then the moisture comes in from the Amazon, and you get a snow layer. It all falls, and as it accumulates, it turns to ice, and you can start making measurements going back in time. And here's an ice core that's taken out. We haven't made any of these. We haven't made any measurements that bubbles, that once it closes in, after you get about 100 meters of snow and ice, then it closes in, and you have bubbles like this. which the air can't escape, and then it stays that way. We have taken some samples from above after the bubbles have closed in, that is in what's called the fern up above it. Before it's closed, I think it can still move around. But a lot of people have done measurements that show you concentrations earlier. Here's CO2 going back to before the industrial era, and it was around 283, 285 parts per million, and now it's 360. The next slide will show methane, and our measurements now are at 1750, up even higher here, but it was around 700 before the industrial activity. N2O, same thing, was around 275, and now it's up around approaching 310. All of these gases have absorption spectra which tend to trap the infrared radiation, and you can go back even further. At the Vostok core, they're back about 400,000 years now, and what this shows, I have to point it down here, this is about 150,000 years ago. In the last time period before there was a series of ice ages, and then you get back to an interglacial back here. We're in an interglacial right now, and you can measure the average temperature there by the oxygen 16, oxygen 18, or the deuterium hydrogen ratio, and that's what gives you this graph here that shows the onset of various ice ages and then back to into this interglacial. Well, methane was as high as 700 in the interglacial and as low as about 300 during some of the ice age. Carbon dioxide got down around 200 and as high as 280 in the last here, and then we drop it down back again. And what you see is this is methane went from 300 to 700 for 150,000 years, and now has gone up 1,000 more in a period of about 150 years. Carbon dioxide had varied in this range for that same 150,000 years, and then went up to 360 after that. There are some other factors that get involved. The amount of sulfur that goes in. This gets involved as far as greenhouse warming, because sulfur turns into sulfuric acid in the stratosphere and can reflect and change the albedo of the Earth. In the northern hemisphere, the amount of sulfur dioxide that's formed has, the natural flux here has been overwhelmed by the regional fluxes. In the U.S., which is in red, the number has actually fallen off, but in the other parts, and especially in China, the amounts are going up. But these are regional effects on changing the albedo, and they get involved in trying to model the global warming aspect. Here's a summary of the forcing, that is the intensity, the amount that you're trying, that has to be accounted for, and in tending to increase the temperature of the Earth. And during this time period, in 1980 to 1990, about half of it is from CO2, and then from the other gases that are shown here. Next slide, and I think I have only, this is temperature effects since 1880, and there is a general trend in here of the order of a half a degree centigrade or 1 degree Fahrenheit. There has been a lot of discussion about the how more very, very good. Let's see if there are any more stuff. If you go back into I have to stop here. At one point, when I was at the University of Kansas, I sneaked 2 slides into one of my colleagues who was giving a seminar there, was going to go to the University of Chicago afterward, and I was going to ship them off to my brother who was at the University of Chicago. And I put the 2 slides in, and the first one, well, he was a theoretician, and so I put a slide in and said, what the hell, I thought this was chemistry. And it took about 10 minutes for him to start talking about it. And so I swooped back and took the other one out, because I didn't know it was true. I never did ship them, but very good, Al. The question of what we're going to do about global warming is something start trying to control carbon dioxide emissions. This was a British advertisement. I saw this in Nature in 1991. What had happened was that they had they defined something sort of called the storm that comes up once every 300 years, and they'd had 3 of them in 4 years. And so they were saying, this was the British government actually put it and said, global warming, we have been warned, because one of the aspects of global warming is increased frequency of major storms, increased intensity of those storms. And they were saying, this looks as though something is happening. The insurance companies certainly think so. The coal companies are very much opposed to thinking about it. And so in the current circumstance, what we're doing is talking about global warming and wondering whether we should be doing anything about it. But most of the scientists that have worked on it say that the effect that you expect is a warming of 1.5 to 2 degrees centigrade by the middle of the next century. And that doesn't sound like a whole lot, but it is not very much different than the temperature change in mid-latitudes between now and the middle of the last ice age. So the temperature changes of a few degrees centigrade have major effects around the world, and so this is going to be an important subject all through the coming decades as to what's happening in global warming and trying to understand it better. Thank you very much.
Questions or comments from the audience?
You mentioned that if the temperature goes up, the British claim that all their monsoons were storms were because of that. Now, if you have so much more rain, what does it do to change the chemical composition?
Well, it's not so much you have more rain. If you trace the trajectories of major storms, hurricanes in the Atlantic, typhoons in the Pacific, back to where they start, what you find is that the water temperature is around 81 degrees Fahrenheit. If you don't have that temperature, you don't get major storm. The temperature generally is warmer the further west you go in the Pacific, so the storms tend to start in the middle Pacific. Places like Tahiti have far fewer storms than you have in Japan, for instance. And so if you have global warming, then you should expect more 81 degree water and more 82 degree water. So you should have more storms and they should be more intense. It has to do with the rate of evaporation of water from the ocean surface feeding in, bringing latent heat in and pumping up the storm. So it has a very straightforward physical origin to that particular concern. Chris?
Shay, what happens to the albedo as the temperature cranks up?
The albedo is largely determined by 2 things. One is what's going on in the surface, and and then what happens to the clouds. Now, as far as what's going on at the surface, if you think of a surface that has water and ice, water has an albedo of around 0.1, ice of around 0.8 or 9. So if you end up warming right at that point, what you're doing is converting ice into water. You're reducing the albedo in that particular region from a high value to a very low value. And that's going to mean more radiation is absorbed by the Earth, and that's a positive feedback and that's in all the calculations. If you ask what happens to the clouds, it gets very complicated. And that's because if you talk about a cloud that's near the surface, the top of the cloud isn't much different in temperature than what you have at the bottom. And so the cloud can reflect, and although it will absorb infrared radiation, it will also emit it. And so the cloud that's near the surface tends to increase the albedo. But the cloud that's up high is doing 2 things. One, it's still reflecting, but now it's absorbing infrared and emitting far less radiation out of the top. So, and because the temperature goes up with altitude. So that the question of that calculation is very tricky, because you not only have to know whether there will be more clouds when it warms up, but at what height they'll be. changing the height would have an effect. And that's a very different, you can make various kinds of calculations about this, but checking them in the real world is the problem. And that's where people are trying to devise how to do it at the present time. John?
Early on, when you talked about a number of different sources for methane. Is there a culprit for the increase in methane? I mean, is it?
There is not a firm assignment of it. The number of cows has gone up from 800 million to 1.3 billion since 1950. The area in rice paddies hasn't changed very much, but the number of crops per year has, so the fraction of the time that is underwater has increased. Both of those are likely probably contributors to it. It sort of looks, if you look at our data, it looks as though something happened 20, 25, 30 years ago, and the average lifetime of methane is about 10 years. And so if you shifted somewhat, then it would take a while for it to come to a new equilibrium, and it's sort of slowly asymptoting. When you look at the measurements that the Australians and the Japanese have made in their ice cores, what one finds is that in fact, although methane, what we found it to be going up, it looks for them as though the biggest increase in methane was happening around 1965, and that it's been slowing down ever since when you look at the ice cores. It's certainly been slowing down during the time that Don's been measuring. Right?
Given that it seems unlikely you can stop a lot of the population increase from burning coal in the next century, then are there prospects for things such as an artificial adjustment of the albedo by the propagation of low clouds? Does that seem to be at all feasible?
There have been some discussions of trying to influence the albedo by putting something into the stratosphere, and something that would cause, would interfere there. If you change the albedo, you change the amount of visible radiation that hits your crops. So it's not something that you can do without any effect. Something that can be thought about is, so far is very expensive, is not to have carbon dioxide get to the atmosphere, but to trap it in the major power plants. Now that involves having materials that are there to react with it and putting them back in storage, back where you took the coal out or something like that. There's supposedly a plant in Japan where they're doing that, just to find out the conditions about that. But it's obviously not being applied worldwide. But if things get pressured enough, then that's a possible kind of solution.
Well, this morning, several times, there's an article about banning certain paint solvents, oil-based paint solvents.
The question of oil-based paint solvents in Los Angeles area, that has to do with still another problem, which has to do with the formation of tropospheric ozone, which is a major ingredient of smog, and that's another area that we're working on. Oil-based paint solvents in the Los Angeles area are supposed to be one of the important sources of organic chemicals. And if you have organic chemicals and you have simultaneously nitrogen oxides, you get the nitrogen oxides from automobiles, then you have a mechanism for producing ozone in the lower atmosphere. And that's a major ingredient, a major component of producing smog. If you're trying to control this, then you need to control both the nitrogen oxides and the organic chemicals. And it's certainly one part of it. We've been doing, we're just looking at some data from Santiago, Chile, that Don and Tai Chen and Jimmy Lopez collected in Santiago a few months ago, and they're going back next week, where we see a lot of hydrocarbons that come from burning, from takes a long time. The question becomes one of equilibration into the ocean as carbonate and bicarbonate, and eventually of carbonate crystallizing out of the bottom. So that the time scale, as I remember calculations earlier, when started looking ahead to the year 2100, this is from 20 years ago, looking ahead to the year 2100 when all the fossil fuels have been burned. But the scale at which they plotted it went to 3,000. So it was a slow process.
Well, let's thank the speaker again.